Okay, so calculus had been developed. We've got Newton, we've got Leibniz, we have other contemporary mathematicians working hard to see what calculus can do and all the applications that calculus could have to physics. And there was an Italian mathematician named John Bernoulli. So his name is kind of important for you to know. Okay, John Bernoulli, Italian. He figured out that calculus could be used to prove certain limits. So up until this point, the limit that we know we've memorized, the limit of sine of x over x as x approaches infinity. Okay, what do you know that limit value to be? This is approaching infinity. Okay, approaching infinity is 0. That had already been proven. That had been proven with what we called the sandwich theorem. The other limit, the limit when x approaches 0 of sine of x over x, which we know to be 1, up until that point was unproven. They had a pretty good hunch it was going to be 1. They looked at a graph. They thought it was going to be 1. Everything pointed to the fact that it would be 1, but nobody could prove that it was going to be 1. And the biggest sticking point happens when you plug in 0. When you plug in 0 to a problem like that, what do you get? Tell me literally, what do you get? Don't know. That's interpreting what it means. Literally, what do you get when you plug in 0? Sine of 0 over 0. And what is the sine of 0? 0. So literally, we're getting 0 over 0 when we plug it in. That is called an indeterminate form. That vocab word is something that you're going to need to know. All right, indeterminate. An indeterminate form. It means it cannot be determined. There are several, I should pluralize that, there are several indeterminate forms. The most common is 0 over 0. That is called an indeterminate form. That means it's not proven. Another is infinity over infinity. These are forms that fail all the rules because the rule says, hey, if you divide any number by itself, it's always going to be 1, except 0 over 0, except infinity over infinity. Okay, so these are called indeterminate forms. All right, what do you get when you subtract a number from itself? Yeah, you think so, right? Not true. Not everything, because what's infinity minus infinity? Okay, that's not 0. And so that's called indeterminate form as well. You've also been told that when you multiply any number by 0, what do you get? 0, except when you multiply 0 by infinity. Okay? Well, which one wins? The 0 or the infinity? Because you've been told every time you multiply a number by 0, it's 0, but you're also told every time you multiply a number by infinity, it's infinity. So what happens when you multiply 0 times infinity? Which one wins, the 0 or the infinity? Okay, that's another indeterminate form. All right, so there are many. There's a whole, if you Google indeterminate forms, you'll get a whole bunch. These are the 4 we're going to deal with. And until calculus came around, they couldn't prove any of these. They couldn't prove the results. And then John Bernoulli figured, hey, I think we can use calculus to do this. All right, so here is John Bernoulli's rule. John Bernoulli said, if you have any function over a different function, kind of like sine of x over x, and you try and take the limit of that as x approaches anything, if that comes out to be an indeterminate form, he said, I suggest you try using calculus. So if that doesn't work, then try the derivative over the other derivative, and then try the limit and see if that works. And see if you can plug in your a value to that. But if you happen to get indeterminate again, then try it a second time. And then take the second derivative over the first derivative, over the second derivative, and take the limit approaching a of that and see what you get. And just keep doing successive derivatives over and over and over again until you finally get something that is determinate, not indeterminate, which means you actually get a value. So you're going to repeat until you get a determined value. This is John Bernoulli's rule. Okay, so it's pretty important. We're going to give the guy credit for it. And that was in Italy. L'Hopital read about this rule. Okay, letters, papers, people going back and forth. He was pretty jazzed about this rule. Oh, this is pretty awesome. He's like, well, I wonder if that would work on the other indeterminate forms, like not just 0 over 0 and infinity over infinity, but what about some of the other indeterminate forms, like the subtraction, and what about the multiplication? And so L'Hopital did a little more work, and L'Hopital found that it worked on the other indeterminate forms as well. So L'Hopital published another paper saying, hey, guess what? I used John Bernoulli's rule to do this, and he did more stuff, and he published his own. Well, as history would have it, everybody started calling it L'Hopital's rule, even though it wasn't really his. He got it from John Bernoulli. But because L'Hopital published, and John Bernoulli just did his in like letters and papers back and forth, but L'Hopital put it in writing, and he got it published, everybody now calls it L'Hopital's rule, even though it really wasn't his rule in the first place. It was John Bernoulli's rule. But it's all about who puts their name on it and who gets it published. So John Bernoulli's rule is really AKA L'Hopital's. But we want to give credit to Bernoulli because it was his idea in the first place. Okay, it's very similar to Newton and Leibniz. They each had their own ideas, and it was just really a question of who published first. And in this case, L'Hopital is the one. So only recently, like since the year 2000, have books started giving credit back to John Bernoulli. It was always L'Hopital's rule, L'Hopital's rule, L'Hopital's rule. And now if you look in your book, it'll say L'Hopital's rule, and then there'll be some parentheses, and they'll talk about John Bernoulli, and they'll give him the credit too. All right, this is a fantastic rule, and we can use it to prove all the limits that we weren't able to prove before. All right, so here, what do I need to do? Show how it works with some examples. So let's start with that basic sine of x over x example. I wish I could have taught you this when we were doing limits, but you needed to know derivatives, and we didn't know derivatives yet. So now we're going to kind of combine the limits and the derivatives. So sine of x over x as x approaches 0. Clearly, when we plug in 0, we get sine of 0 over 0, which is 0 over 0, which is an indeterminate form. Because this is an indeterminate form, it's legitimate for us to apply L'Hopital's rule. It would not be correct for you to apply L'Hopital's rule to every problem. It only is applicable when it's an indeterminate form. So the rule says, all right, find the first derivative of both the numerator and the denominator. So what is the first derivative of sine of x? Cosine of x. And the first derivative of x? 1. Yeah, dx, which is 1. And now let's plug 0 into that. And we get the cosine of 0 over 1, which is 1 over 1. And we get a determined form, which is 1. And that was the first proof that this limit existed. So what we're going to do is we're going to continue just practicing applying L'Hopital's rule. This rule is fun and powerful, and it's great to use. The danger is that you would apply it in an inappropriate situation. Okay, just keep reminding yourself it is not appropriate to apply it to all limits. It only is appropriate to apply it to limits where the derivative doesn't exist. Okay, so let's try the limit as x approaches 0 of, what do I have here? 3x minus sine of x over x. Always check the value first. So when we plug in 0, we're going to get 3 times 0 minus sine of 0 over 0. So again, I do get the indeterminate form 0 over 0. Because I got the indeterminate form, then I can apply L'Hopital. So when we take the derivative now, we're going to have the derivative at the top, which is 3 minus cos x over 1. And I can plug 0 into that, which will give me 3 minus cos of 0 over 1, so 3 minus 1, or 2. And I get a determined form. A third example. Let's take the limit as x approaches 0 of x minus sine x over x cubed. We check the determined value of this. Does it have a value or not? And so you'll see 0 minus sine 0 over 0 cubed. Again, an indeterminate form, 0 over 0. We're going to get to some of the other indeterminate forms in just a minute. So it would be appropriate to apply L'Hopital here. So when I take the derivative, I'll get 1 minus cosine of x over 3x squared. And I'll apply 0 there. That'll be 1 minus the cosine of 0 over 3 times 0 squared. That's 1 minus 1. Which again gives us the indeterminate form 0 over 0. So I have a second indeterminate form. That means I can apply L'Hopital a second time and successively until I finally don't get an indeterminate form anymore. So now we take the derivative again. The derivative of 1 minus cosine x is sine of x over the derivative of 3x squared, 6x, plug in 0, sine of 0 over 6 times 0 is a third indeterminate form. And so I'll apply L'Hopital one more time. The derivative of the numerator is cosine. The derivative of the denominator is 6. Now I plug in 0, so cosine of 0 over 6, which finally gets me a determined value of 1/6. All right, let's see how L'Hopital is applied in some of the other indeterminate form situations. So let's consider the limit as x approaches 1. And the function we're going to look at is 1 over the natural log of x minus 1 over the quantity x minus 1. We will try directly substituting into that equation. So my limit as x approaches 1 of 1 over the natural log of 1 minus 1 over 1 minus 1. What's the natural log of 1?
0.
Okay, so I have 1 over 0 minus 1 over 0. So that's infinity minus infinity, because 1 divided by 0 is infinity. And then minus another infinity, and that is an indeterminate form as well. So we need to go back and apply L'Hopital's rule. Now, in order to apply L'Hopital's rule, it has to be a numerator and a denominator. It can't be a subtraction problem like what I have right now. So I need to make this function into the form of a numerator denominator. So here's where you're going to have to do some algebra. Some of the algebra in your homework is going to be pretty heavy hitting. You're going to have to do quite a bit of algebra first before you do your calculus. So when we want to apply L'Hopital's rule, we have to convert the subtraction problem into a numerator divided by a denominator. So how are we going to do that algebraically? Before we do our calculus, we got to go back and do our algebra. Joanne?
We can make the common denominator.
Okay, we need to come up with a common denominator. All right, so in looking at 1 minus the natural log, or 1 over the natural log of x minus 1 over x minus 1, we need to create a common denominator for that. All right, that is going to give me 1 over the natural log of x. That will be multiplied by x minus 1 and x minus 1 minus the 1 over x minus 1. It needs to be multiplied by the natural log of x times the natural log of x. So I do have to do some algebra here in order to get it into the form that L'Hopital would apply. So that will give me a numerator of x minus 1 over a denominator of natural log of x and x minus 1 minus a numerator of the natural log of x over a denominator of the natural log of x and x minus 1. That becomes x minus 1 minus natural log of x over the quantity natural log of x and x minus 1. So what started out as a fairly simple subtraction problem has now become kind of a mess of an algebra problem, but at least it's in the format that L'Hopital would apply. Because until we get a single numerator over a single denominator, we can't use L'Hopital. So now we're ready. So this was sort of like a little algebraic sidebar here to get us ready for the calculus. So this was our algebraic work that we had to do to get ready to do the calculus. So now we're ready, because we know this was an indeterminate form, we're ready to apply L'Hopital's rule. So let's put the limit back in, and then remember the limit was as x approaches 1. And we want to take the derivative of the top over the derivative of the bottom. So what is the derivative of the numerator? 1 minus, technically 0, and then minus 1 over x. The denominator, how do I take the derivative of that denominator?
Product rule.
I need the product rule. All right, the product rule tells me that I'll have x minus 1 times 1 over x dx dx plus, so I'm going to have to extend this out again, the natural log of x times dx over dx. Let's clean that up a little bit. So we have the limit as x approaches 1. My numerator will just be 1 minus 1 over x. My denominator, as I clean that up, would be, Joanne, you want to try?
Yeah.
Okay.
Natural log of x plus x over 1 over x minus 1 over x.
Yeah. All right, let's plug 1 into that. So I'm going to get 1 minus 1 over 1 over 1 minus 1 over 1 plus the natural log of 1. That gives me 1 minus 1 over 0 over 1 plus 0. In other words, a different indeterminate form. So the first time I did it, I had the subtraction indeterminate form. The second time, now I have a different indeterminate form, which basically tells me I need to do it again. Okay, this next time it works. But is it currently in the format that I could take the derivative? Is it a numerator separated by a denominator? The answer is yes, so that's okay. If you don't mind, I am going to clean it up though algebraically before we start taking. I'm going to get common denominators because it's going to really help us to clean up our algebra so it's a little bit more simple before we take our derivative. So again, we're going to take another algebra sidebar. Let's get common denominators. So in my numerator, I'm going to need to multiply x over x so that it has a common denominator. In my denominator, I'm going to multiply also x over x so we have a common denominator. So I'm going to do some more algebra before I do any more calculus. So my numerator becomes x minus 1 over the common denominator x. My denominator becomes x minus 1 plus x ln x, also over the common denominator of x. And what's the rule about dividing two different rational expressions? Multiply by the reciprocal. And so what this allows me to do is have x minus 1 over x times the reciprocal of x over x minus 1 plus x ln x, which reduces. So I'm left with the limit of x minus 1 over x minus 1 plus x ln x. And that's a little bit more simple. That was some algebra, so now I can do my third round of calculus, or my second round of calculus. I've done, oh, it froze up on me, on you. Pause the recording a minute. All right, let's take the derivative of the numerator. Easy peasy. What's the derivative of the numerator? Aren't you glad we're not doing the quotient rule to this? Yeah. Okay, L'Hopital is just straight out derivative. It's what we wish the quotient rule was, but it's not. All right, what's the derivative of the numerator? 1. What's the derivative of the denominator? 1 plus. All right, now we got to do x ln x, which is going to be product rule. So it'll be ln x times dx dx plus x times 1 over x dx dx. So that's going to clean up really nicely for us. My numerator, thankfully, is just 1. My denominator becomes 1 plus ln x plus 1. And we're plugging in 1. So we get 1 over 2 plus the natural log of 1. We know that the natural log of 1 is 0. So phew, we finally get 1/2, which is a determined form, not an indeterminate form. All right, last one. All right, let's look at the limit as x approaches infinity of 1 plus 1 over x to the x. All right, let's just try substituting that in and see what we get. So we're going to get 1 plus 1 over infinity to the infinity. That is 1 to the infinity. And you think you know what 1 to the infinity is? But you don't. Okay, this is another indeterminate form. So we need to apply L'Hopital. Now, we're going to apply L'Hopital in a little bit of a new way. What do you notice about the original problem that's similar to something we were kind of just doing in previous, like right on the quiz? We've got a variable in the base and we have a variable in the exponent. All right, what did we do then? What was our first step? Logs, and that's going to be our first step here as well. We're going to apply logarithms here to help us get this into an algebraic state that we can actually work with. All right, so we are going to apply, this is going to become the limit as x approaches infinity. If we put a logarithm around this problem, what does that allow us to do? Bring the x to the front. Okay. However, that is still not in a quotient format. Okay, it's still not in a quotient format. So, because remember, L'Hopital has to have a numerator and a denominator. So I'm going to switch the order on you a second. I'm going to put times x. Remember how when we wanted to change division into multiplication, we multiplied by the reciprocal? How do you change multiplication back into division? You divide by the reciprocal. And so I want to change this back to division. And so I'm going to have the natural log of 1 plus 1 over x divided by, instead of multiplied by x, it will be divided by 1 over x. Now I can use L'Hopital because I am in a numerator over denominator format. All right, let me take, yeah.
Can you also can you divide it by x to the negative 1?
Sure.
It's the same way.
Yes, yes, you can write it as x to the negative 1 if you'd rather have it be, oh, it's not letting me erase, why not? Yeah, if you wanted that to be x to the negative 1, that would be fine. Okay, all right, now we're ready to take our derivatives. So we're going to apply L'Hopital to the derivatives now. All right, in order for me to take the derivative of 1 plus, or the natural log of, I've got 1 over 1 plus 1 over x times ln e times the chain rule, which is 0 minus 1 over x squared. That's the numerator derivative. What's the derivative of the denominator?
Negative x to the negative 2.
Which is negative 1 over x squared.
So we can reduce.
Yes, we can reduce. If I've got 0 minus 1 over negative 1 over x squared and negative 1 over x squared, we can reduce both of those. So we are thankfully now left with 1 over 1 plus 1 over x, and then I don't need ln e. All right, let's plug infinity into that. 1 over 1 plus 1 over infinity. That's 1 over 1 plus 0. So that's 1. Here is where a multiple choice problem absolutely just drives you bonkers, because you'll see the number 1 as one of your options on your multiple choice. You'll have done all this work and you'll see the number 1 and you'll choose it. Yes, it's 1. I got my limit. What was the first thing we did? Very first thing, we applied a logarithm. So this is not the true answer to the limit. We got to undo the logarithm we applied. We applied a natural logarithm. So the actual limit, we have to undo what we did. How do you undo a natural logarithm? E to that. So the actual limit value to preserve, if you did something, you have to undo it. That's math. If you add, you have to subtract it. It always has to be balanced. So the actual limit would be e to the first. So you could have done, so the answer is e.
Yeah,
So you could, that's the actual limit to the original problem we started with. The only reason we did a natural log was because we had a variable in our base and a variable in our exponent. And we needed to do a natural log as part of our algebra to help us do our calculus. At the end, you have to undo what you did to get your actual answer. So that's where a multiple choice, because they'll have both the number 1 and the letter E as options, and you got to choose the right one.
But I still don't get it why it's E for why it's that.
Because all of this from here on down to here was all because we took the natural log. That's the only way it made it work. So all of that is the result of having the natural log. Here, let me write